Hello, my name is Nurul Faraina binti Mustafa Sharafuddin, metric number AA201123. We are from group 7. This group consists of Nur Edina Ashikin binti Muzamir, Ongkangnen. In this video, we will talk about shear force and bending moment. So, enjoy watching our group presentation video.
So I will start for the first part, which is introduction. Beam is a slender bar that carries and supports transverse load along the longitudinal axis. Beams are generally long, straight and prismatic. The applied forces are perpendicular to the bar, and it consists the shear force and the bending moment in internal force. There are 6 important types of beam, which are cantilever beam, simply supported beam, overhanging beam, continuous beam, fixed-ended beam, and the last one is cantilever with the simply supported beam. Transverse loading of beams can classify as concentrated loads or distributed loads. Concentrated load acts relatively in a smaller area. For example, the force exerted by a chair or table leg on the supporting floor, or the load exerted by a beam on a supporting column. While for the distributed load, it is acts spread over a large area. It is always converted into its equivalent concentrated load, acting at the center of gravity of the loading. For example, the water pressure on the bottom slab of a water tank. If the floor slab is supported by beams, the load on the beam is certainly uniformly distributed. Moving on to the second part, which is the theory and the literature review. Shear and the bending moment diagrams are analytical tools to help perform structural design. We need to determine the value of shear force and bending moment at a given point of a structural element. For shear force, if the right side is tending to move upwards, shear force will be positive, otherwise it is considered as negative. While for the bending moment, if the beam is bent from concave to upward at the left side, it will be a positive sign. Otherwise, the bending moment is negative when the beam is bent from concave to downward. To determine the maximum shear and the moment, express shear force as B and bending moment as M as position X along the axis. It can be represented by shear force diagram and bending moment diagram. There are 2 relations of beam with uniformly distributed loading. For the first one is between distributed load on the loading diagram and the shear diagram. Slope of the shear diagram is equal to the magnitude of the distributed load. For the second relation is between the distributed shear force and the bending moment. Slope of the moment diagram is equal to the magnitude of the shear diagram at that distance. Point load lead linearly varying moment diagram, while for the constant distributed load will lead quadratic moment diagram.
Next, I will talk about methodology. Shear force and bending moment data could be plotted on several graphs. It is simple to view various value, magnitude, and place. Shear force diagram and bending moment diagram are required by designers when deciding on the shape and size of a beam. For example of a simply supported beam with a point load. First step is draw the diagram to show the shear force and bending moment as shown in the first picture on the slide. And the second step is find the direction of a simply supported beam, and then both direction will be the same because the beam is symmetrical. R1 and R2 equal to W per 2 equal to 1000 kg. Third is determine the shear force at point A, B and C. When a point load is carried by a simply supported beam, then in parts find the shear force value. The shear force value will remain constant until the point load is reached. The shear force at point load varies and remain constant until another point load is applied. Like A to B 1000 kg, B to C 1000 minus 2000 equal to negative 1000 kg. And then the bending moment at the support will be 0 in the case of simply support beam, and where the shear force is 0, it will be at its highest. At point A and C, it will be 0 for moment B equal to 1000 multiplied 2 equal to 2000 kgm. So next one is example of uniformly distributed load and a point load. First, draw a diagram of shear force and bending moment for a simply supported beam carrying a uniform distributed load and point load as shown in the slide. Second, we need to find R1 and R2 of a simply supported beam. There will be no difference in direction because the beam is symmetrical. So the R1 and R2 is 1000 kg. Yeah, and then next, shear force is at the left side of point C. Because of uniform distributed load, the value of shear continuously varies from point B to C. So the value is equal to negative 1000 kg. For the shear force diagram, what we see, the shear force is maximal at point A and remains constant until point load, as can be seen from the graph. Because of the point load, the shear force value at point B drops. Because of the uniformly distributed load, shear force decreased from B to C. Shear force steadily decreased at point C due to point load. Shear force is constant from point C to point D since no other point load is acting in this range. And for the bending moment, at support the bending moment it will be 0. MA and MD is 0. So at the point B and C will be 1000 multiplied 2 and equal to 2000 kgm. Then the maximum bending moment will be at the point where when the shear force is 0. As a result, the bending moment will be greatest at the midpoint. The moment maximum is 2400 kgm.
Hi, my name is Omar and I will present the analysis and discussion of our project. So this is the example question we take from internet website. A simple beam AB is loaded by two segments of uniform load and two horizontal force acting at the end of a vertical arm, as shown in the figure below. Draw the shear force diagram and bending moment diagram for this beam. From this figure, we can conclude that this is a simple supported beam, and in this figure, there are two uniform distributed load acting and two force acting on it. First of all, we need to convert the figure into free body diagram, and the two horizontal force had become a bending moment acting at the middle of the beam. Next, we convert the uniform distributed load into point load. So we multiply 4 km per meter with 2 meter. So the answer will be 8 kilonewton. The distance of point load is half of the distance of uniform distributed load. So the distance of point load is 1 meter, which means that the point load is acting 1 meter to the right of point A and 1 meter to the left of point B. After that, we find the unknown force. We first apply the concept of equilibrium of force on y-axis, but there still exists two unknown forces. Then we apply the concept of equilibrium of bending moment at point A. So the value of RB can be found, and we substitute the value of RB into this equation, and the value of RA also can be found. Now we have all the value of forces, and now we can plot the shear force diagram. Shear force diagram need to plot it from the starting point, which is 0, And from the calculation just now, we know that the value of RA is equal to 6 kN. So the value of shear force at the starting point is equal to 6. Next, along the first 2 meters, there exists a uniform distributed load, and just now we had converted it into point load, which is 8 kN. Thus, the shear force will drop until -2 along this first 2 meters, and the shape of the graph of the first 2 meters is linear because it is uniform distributed load. After that, along the next 4 meters, there exists no any forces. Thus, the shear force diagram will remain constant along this 4 meters. Lastly, the condition of shear force at point B is same as point A. Thus, the shear force will drop again by 8 until -10, and lastly back to 0 because the value of RB is equal to 10 kN. For bending moment diagram, it also starts as 0. The bending moment at 1.5 meter right of point A is equal to the area under the shear force diagram, which also equal to 4.5 kN/meter. And the shape of the graph is parabolic. For the next 0.5 meter, the bending moment also is equal to the area under the shear force diagram, but it is decreasing because the area under the shear force diagram is below 0 on the shear force diagram. For the next 2 meter, 4 kN/meter is added with the product of shear force as at 4 meter right of point A and distance, which will be equal to 0, but there exists a 16 kN/meter bending moment, so we needed to add with the bending moment at this location, so the final bending moment will be 16 kN/meter. For the bending moment at 6 meter right of point A, we just added with the product of shear force and distance at this location, while for the bending moment at point B, we just deduce the area under the shear force diagram, and the final bending moment will be equal to 0 and back to 0. The method we use to solve and analyze this problem is called graphical method.
Okay, the last one is conclusion. A shear force diagram can be used to examine the beam. The shear force diagram shows the shear force that the beam segment receives over its length. The bending moment shows the bending moment that the beam section receives along its length. Shear and bending moment diagram are analytical tools that are used in conjunction with structural analysis to determine the value of shear force and bending moment at a specific position of an element. The kind and size of a member of a given material can be easily determined using this representation. Another use of shear and moment diagram is to calculate deflection using the moment area method of conjugate beam method. Shear force diagram and bending moment diagram give designers an overview of consequences of a combination of force and their probable effects on the structure and its stability, as well as likely contractional restriction to consider while designing. So that's all from us. Thank you.